So hi everyone, I'm extremely happy to be here. I will give an introduction to differential linear logic. So the content of the talk might be known and very well known to an important part of the audience. My goal here is that for some of you who don't know about linear logic, you will be able to get an idea of what differential linear logic is at the end of the talk. So please excuse me in advance if you know what I'm going to talk about. And if you don't know what I'm talking about, please do not hesitate to interrupt me. I am more than happy to detail a few things on the backboard. My talk so I have been very generously given 1 hour and a half, but I might not use this whole hour and a half, so please do not hesitate to interrupt me. I'm happy to take any questions during the talk or after. And it doesn't work.
Use the keyboard.
Use the keyboard, okay. It was working 5 minutes ago. So this is going to be maybe a blackboard talk at the end, after all. Ça work? Okay, Karma, yes. So thank you to the organizers, to the wonderful organizers for putting in the hours to bring us all together here. I think we're all extremely happy to be spending a week at the CIRM and to talk about differentiation. So again, thank you for the hard job of organizing a conference week. So my objective here is to make differential linear logic a comfortable place to think for you. So differential linear logic at the beginning was described with nets, with proof nets, with interaction nets. It can also be described by sequence calculus. It can also be described by its categorical semantics. This is what Jean-Simon will talk about tomorrow. I will try and take the approach of sequence calculus, but because I am very, very much a semantician at the heart, I will be annotating everything with some kind of informal semantics that I will give you a few intuitions about the semantics of differential linear logic while explaining its syntax. The semantics will stay quite informal for a very, very long part of the talk. The rigorous semantics will be given tomorrow, I think, by Jean-Simon Lemay. So I will begin by a quick reminder of linear logic. Is there someone here who's not comfortable with linear logic? I think there is. That's the time. Yeah, maybe. Okay, so my goal here is to speak to you. If you're coming from type theory, if you're coming from logic but not linear logic, this is something that exists. This is for you, so please ask questions if you're not comfortable with what I'm saying. If you're a mathematician and you're not quite comfortable with linear logic, please ask questions if I'm not making everything perfectly clear. I will give the rules of differential linear logic, comparing them to the one of linear logic, and most importantly, I will give a detailed explanation of its cut elimination procedure. What's interesting, what I find very, very nice in differential linear logic, it's dynamics. It's a logical dynamics given to mathematical calculus in a higher order way. It's extremely well presented, and it gives us, I think, a lot of nice insights about calculus and mathematics. I will also give an introduction, a quick introduction to differential lambda calculus. So this has not been presented this morning. You saw a more modern version of differential lambda calculus, which is called resource calculus, which works maybe a bit better, but there are interesting stuff in the first version of differential lambda calculus that I will detail, and I will compare them a bit to differential linear logic. And at the end, if time permits, I will detail a few models, a few concrete models of differential linear logic, just to give you a bit of insight of the computations you can find. Okay, linear logic. And I will only speak about the call by name interpretation of intuitionistic logic in linear logic. So the basic, very basic idea of linear logic is that you have two kinds of functions, two kinds of proofs, two kinds of implications. You have linear implications, which is like the linear functions we all know in algebra, and you have the nonlinear implications, which might describe more interesting, more complex computations in math or in computer science. And the most interesting idea is that the link between the two, so we all know that some functions are linear and some functions might not be linear if we step outside of algebra. The very beautiful idea of linear logic is to use a new connector to relate the two. And this connector is called the bang, the of course. It's one of the exponential connectors. And it's described with these symbols. So that's the very basic. And the rules of linear logic will detail a lot of stuff, but will detail principally how this connector interacts. And differential linear logic will add to these rules to describe how differentiation at higher order works. So again, the very basic idea about proofs is that if we provide a proof of this sequence, then this proof will be linear in A. It will be interpreted by a function which is linear in A. A proof of this sequence will be nonlinear, interpreted by a nonlinear map. For example, a polynomial, for example, a power series, for example, something that we can differentiate. And one of the the first rules, and I would say the most important rule, is that something which is linear, is that one can forget about linearity. If you have a proof which is linear, then you can transform it into a nonlinear proof. And this is the kind of stuff one can write in linear logic. I have a linear proof, and I'm forgetting that it is linear, and it is just a proof. There is an intuition about resources here that you have heard a lot about already this morning. A proof or a program that is linear will use exactly once its hypothesis. A proof which is a proof of this linear sequence here will make use exactly once of the hypothesis A. It needs to use it, but it will use it only once. A proof of that sequence might not need to use A at all, and it might use it several times. And that's a basic resource intuitions. Linear logic. For the vast majority of the talk, I will not care about everything here. I will only care about exponential connectives. I will very, very much focus about linear connectives, but just so you know that this is a syntax of formulas. We have two additions, two conjunctions. We have multiplicative connectives. We have additive connectives. We have positive formulas. We have negative formulas. There's a lot of stuff that can be done. I won't go in detail of that. The important stuff is that I will be placing myself in a, I'm not managing that very well. I will be placing myself in a classical setting, meaning I will use negation as much as I want, and I will use it a lot. Formulas are equivalent to their double linear negations, because this is how it should be in a linear world. I have strong opinions about negations in linear logic. So I will be using in different ways bilateral sequence as they might be used in intuitionistic linear logic, or monolateral sequence, depending on what I want to interpret or how I want to describe the rules. We have involutive linear negations, and I think the one thing that I am interested in is this line here. We have two exponential connectives, bang and a why not. The why not is dual to the bang. We will see, I already gave you a few intuitions about the bang. I don't know if we have seen it this morning, I'm not sure in fact. The idea of the bang is that we have an arbitrary amount of resources in the bang. The why not is the dual of the bang, and we will see more about that in a minute. again, these are the rules of linear logic, multiplicative additive linear logic. I will not go into details about that, but just know that there is something that looks very much like a coproduct. It's some kind of disjunction, and it is a coproduct. We have something that looks very much like a tensor product, and it will be interpreted by a tensor product in this model. We have something that is denoted like that, and I don't know why, because it should really be a Cartesian product. We have something else. Well, it's written like that because it's a dual of the pair. We have something that's a bit mysterious here, but in fact it is some notion of completed tensor product, but we won't go over that. And again, the important stuff is that implicitly we have conjunctions in the hypothesis and disjunctions in the conclusion. So we have tensor here and pairs here, and that's the only thing you need to know about. And of course, the negation here is linear, meaning the negation, the duality is just the implication of the force linearly. Okay, and that's linear logic in a nutshell. So I think I already told you about that. What do we need to know? That we are going to interpret proofs, so either a proof of the fact that A implies B, or a proof that I have not A or B. Both of them are going to be interpreted by linear maps. Linear maps in some structure where I can speak about linearity, and there are several different structures where I can speak about linearity. And nonlinear maps will be interpreted as nonlinear proofs will be interpreted by nonlinear maps. And these nonlinear maps will be continuous, will be differentiable, because we are interested in differentiation, and we have several forms of nonlinear maps. Okay, so now I'm going to go far away from the resources intuitions you have heard about this morning, and I'm going to give you my interpretation, not my interpretation, but my preferred interpretation for the why not connectives. So the idea behind the why not connectives is that when we are using the why not, we are speaking about functions. We are speaking about nonlinear functions, and we are going to describe operations on nonlinear functions. And linear logic is very much about speaking about nonlinear functions in a linear setting, in a linear way. So terms of type why not A are functions, smooth functions, nonlinear functions, differentiable functions, some kind of nonlinear functions acting on the dual of A. So if I have an object of type why not, I will annotate it with a nonlinear function that I will denote by F or by G. If I have a proof with a Bengay in the hypothesis, I will do the same. I will denote it with a nonlinear map. And now we can look at the rules for linear logic. So we have 4 rules, which have, like all of them have, can be described in terms of resources, but they can also be described in terms of smooth functions, in terms of differentiable functions. So there is a weakening which says, well, if I have a proof then which does not depend on A, then I have a proof which depends on Bengay, meaning I'm allowed to use Bengay 0 times. I would not be able to write that without the Bengay. I would not be able to use that without the exponential connective. If I have a proof which uses twice Bengay, then I have a proof which uses once Bengay. Again, the number of Bengay doesn't matter, and in the resources interpretation of Bengay, this just tells me that I can glue everything, every bag of resources together. I have the dereliction rules that I already told you about, and I have the promotion rules, which, in terms of resources, tells you, well, if I used infinitely many times my hypothesis to prove A, then I am able to prove Bengay, meaning I can use infinitely many times my resources to prove an arbitrary amount of times the formula I want to prove. So these are, I guess this is the traditional interpretations of linear logic. This is interpretation in terms of resources, which describe extremely well what goes on in quantitative semantics. I think this matches quite well what you heard about this morning. In a classical presentation, we could also very well write that in a monolateral presentation. And well, I'm more interested in that monolateral interpretation, in fact, because that monolateral interpretation gives you operations on functions. So now I will describe the other way to look at linear logic rules in terms of functions. And it will be easier afterwards for me to go into differentiation once I know quite well what linear logic does tell me about functions. So weakening. I have something in which I might not have a, and I want to construct a function which goes a scalar function on a, on the dual of a. Sorry, something which takes something of type dual of a and gives back a scalar. Well, the very straightforward way to do that is to say, hey, I will just take the function that doesn't compute, the constant function. So what weakening does, it does introduce the constant function at 1. 1 being an object in bottom. This is not, not very well chosen. The basic idea that I wanted to introduce later, but I think I need to introduce that now, is that for me, this interpretation of false, I will interpret that by the field of scalar. Like, it might be the field of complexes, but let's just work in a real analysis today. So what weakening does, it does introduce a constant function. Okay, if I have, let's see what contraction does. If I have two scalar functions and I want to make them one, then I will just make the scalar multiplication of it. This is possible again because both functions have type. Both functions have type. Have this type, so I'm going into the field of scalar. I mean, the easiest way to do is to just take their multiplication. Well, dereliction is a bit harder to see. Here it very much depends on the fact that we are in a classical setting. But basically, if I have a vector of type A and I want to make a map of it, this map will be linear, but I am forgetting that it is linear. I will just take the evaluation at this point. So dereliction is about evaluating a linear map at one point. Promotion, in fact, you can see looks a bit like dereliction, but involves non-linearity. And promotion is really about evaluating a function at one point. So here I take a vector and I'm constructing the Dirac, meaning the operation that takes a function and evaluates it at a point. And we will go back on Diracs another time. So I gave you an interpretation in terms of resources. I gave you an interpretation in terms of functions. The interpretation of functions is also very well described for bilateral sequence. And it's, in fact, easier to see it that way. There's a small difference here, meaning when you see contraction in a bilateral way, it is much more about identifying two arguments of a function in order to make it a function of one argument. You can prove that this is a dual point of view on the rules I just described earlier. But otherwise, weakening is about the constant at 1, dereliction is about forgetting linearity, and promotion is about evaluating nonlinear maps at one point. Okay, so linear logic is about nonlinear functions. We already knew that. What I want to tell you about today is that linear logic is also very much about distribution theory. So there is an intuition, a first intuition about Bungay being a bag of resources. that you can use 0 or 1 or twice or an arbitrary amount of time. The dual point of view is that Bang A is a space of distributions. And why is Bang A a space of distributions? Because it is a dual of a space of functions, and this is, by definition, a space of distribution. And the rules of differential linear logic, in fact, fit extremely well, amazingly well in the setting of distribution theory. You might have, when you're opening a book about distribution theory, it does scream differential linear logic in a non-higher order way, not to make any judgment of values here. So, in classical linear logic, Bang is a dual of Y naught. So it is a dual of a space of functions, and duals of spaces of functions are what? These are linear operations that operate on nonlinear maps. The first equation here could have been written like that. And that's a distribution which takes f and does something on f. Typically, it does take f and it evaluates it in V. This operation is linear in F. This is some kind of distribution, putting all arguments about topology and continuity and other arguments aside. Yes, Bang is a space of distribution. Great. What can we do about distributions? I don't know if you remember something that tells you that there is a famous paper that tells you that you can't multiply distribution. For those of you who have taken a lesson in distribution theory, someone might have told you that in a very standard way. You can't multiply distribution. The good binary operation on distribution, the important binary operation on distribution is the convolution product, written with a small star here. And what it does, well, it sums in the domain. The basic idea is that taking the convolution of two Diracs will sum in the Diracs. It is some kind of averages of, it does kind of the average of two distributions in a smart way. Okay, so we have, so we went quite far from resources, in fact, and now we went to functions, we went into distributions, and now we are going to go into differential linear logic. So differential linear logic, is about taking the dual of the first rule we took earlier. I told you one of the first rules you could learn about linear logic is that you can go from being linear to being nonlinear. Differential linear logic is about doing the converse. Differentiation is very much about taking something which is nonlinear and making it linear in a smart way, okay? Not by touching zero or whatever way. It is about finding the best linear approximation of your functions. So I told you about weakening, contraction, dereliction, promotion. I will tell you about co-weakening, co-contraction, co-dereliction, and maybe co-promotion at the end if I have time. So I think so this was done by Thomas Erard and Laurent Régnier 20 years ago, hence the conference. And it's already, this is already a very nice idea, you know? Seeing that by taking the dual of some rule in linear logic, well, you might have differentiation. You need more than that to have differentiation. You need not only to have the type of differentiation, but you need to have the dynamic of differentiation. And differential linear logic is much more about describing the dynamic of differentiation than just to give you A or wrong A, depending on what's interesting to you. So let's see how that goes. So let's see, before seeing about the other rules, let's see about the dynamic. So what's extremely interesting is the cut elimination procedure in differential linear logic. So for those of you who don't know what cut elimination is, I should have made a slide about that. Cut elimination is about taking away the cut rule. And taking away the cut rule means computing the composition. The cut rule is interpreted by the composition of functions, and taking away the cut rule means going into the details of what happens when you compose the rules, when you compose the functions. And one of the nice things to see is that already co-dereliction and dereliction interact nicely, and cut elimination describe one of the very basic rules of calculus, meaning if you differentiate a linear function, well, you're not going to find anything new, meaning one of the possible descriptions of linear maps, which is also, for example, described in differential categories, is that linear maps are those which are equal to their differential at 0, for example, at some point. Okay, so do I have more? So I told you Thomas and Laurent had this very beautiful idea about introducing co-dereliction, and it turns out that other rules are necessary. If you have co-dereliction, then you need co-contraction, then you need co-weakening. And so it's even better than that, meaning once you introduce co-dereliction, then all you need to perform cut elimination is to have the exact symmetric of the rules which you had before, which were introduced for resources notions, for resources, notion of resources. So let's see what co-weakening does, and let's see what co-contraction does. Co-weakening, whoa, there's an ugly, very, very, very ugly typo here. So that's, so what co-weakening does, it does introduce an arbitrary object of type Bangay. Please take out the why not here and put a bang. I hope it's correct here. Yeah, it says. I hope it's correct here. And if you have no distribution at all, if you have no information about your vector space, the space you are working on, there is one thing you can always do. You can build the Dirac at 0. Because we are working with linear logic, in fact, we will always work with some notion of vector spaces. So we will always have a 0 that we can work with. So if you have one distribution, if you have only one distribution, then it is going to be the Dirac at 0. This is something you can always do, and you have always an object of type Bangay, and that's the Dirac at 0. Okay. And what co-contraction does, in fact, well, you have two distributions, and the first thing you would like to do is what's the basic operation on distribution? It's convolution products. And in fact, co-contraction is interpreted by a convolution product on distribution. So if you go into a bilateral presentation, and so this is a rule that can be deduced in a bilateral setting from this first one, you have a simpler way. You don't have to speak about distributions here. Co-contraction is just about summing in the domain of a nonlinear maps, Okay, and likewise, you don't have to speak about Diracs if you really don't want to speak about Diracs. And co-weakening is just about being able to evaluate a function at 0. If you can do one thing on distributions, that you can always take the Dirac at 0, and you can always make the convolution at 0. What you can see here, maybe that co-weakening is a neutral for co-contraction. Like the Dirac at 0, summing with 0 gives you nothing. So the co-weakening is a neutral for the co-contraction. As before, weakening was a neutral for contraction. For structural rules, we had constant at 1 and scalar multiplication, and multiplication by 1 gives you nothing. So it's very much of a pattern here. Okay, and of course, these are the rules that I already gave you. I think I gave you that in a bilateral way. You can also make differentiation, turn differentiation into a distribution. if you have a vector, then you can define the distribution that takes a function and differentiate along this vector at a point 0. And that's the intuition behind codirection. Okay. So, like, it's nice. We have the rules, but you don't have anything if you just have the types. I wouldn't be able to claim that this is defining differentiation if I only add these rules. There's a lot of ways to make a function linear. One way is to replace it by 0, for example. It could work. So what is really going to tell us that we are doing differentiation now, we are doing differentiation in a typed way, in a higher order way, is describing the cut elimination procedure for differential linear logic. And let's go into that. I'm not sure I will show all of the rules. I'm most and for all interested in the rules which are mixing structural rules and co-structural rules, meaning something with co-something. So let's do a few examples. What's going to happen here? Can you see? I'm just going to perform the operation one after the other. The basic intuition here is that on the right of the thesis symbol, I have something which is kind of a scalar product, which is kind of operating like a scalar product dog. Evaluating two functions at 0 or evaluating one function after the other at 0 doesn't change anything. Yes. So we did contraction and co-weakening. We are going to do weakening and co-contraction. Well, weakening and co-contraction works the same. So syntactically, you would be tempted to do exactly the same. Let's just apply weakening to one distribution and then to the other. And the reason is exactly the same. This works because semantically it does work. If you apply a convolution product on a constant function, then you just land on a scalar multiplication, or evaluating a function of two arguments at 1 is like evaluating each argument at 1. It's the same. Weakening and co-weakening. So do you know? I think most of you know what's going to happen, but maybe some of you don't. What's going to happen here? Well, I'm evaluating a constant function at 0. I could be evaluating at 40 or -2. It would be the same result. It just gives you nothing. Happily enough, it works. Yeah, this is not very clear. My title is not very clear. So here it's weakening and co-contraction. What's going to happen here? What happens when I differentiate a constant function along any vector? Glenn's. Yes, so Giulio did the math. Yeah, 0. Okay, so we have 0 proofs. So differential linear logic is going to be about adding some rules, but also allowing 0 proof. Because, well, if you're going to do differentiation, then you're going to have an additive structure on your set of functions. You're going to have an additive structure on your space of proofs. So you're going to have a 0 proof. And it's exactly the same for co-weakening and dereliction. Meaning, well, I'm evaluating something which used to be a linear map at 0. There's no choice here. It's going to give us 0. Okay, so proofs. So the grammar for formula in differential linear logic is the same. The syntax of proof is almost the same when you add a few rules, but I don't know if it's more important or less, but you are going to allow sums of proofs and 0 proof, which is going to cause some technicalities, which I'm not going to go into details now. So contraction and co-dereliction, this is where the sum is going to happen. So I could choose to go one way, but there's no reason why I should go this way. I could also go the other way to just eliminate the cut rule in the sequence. And behind this necessity for a sum that could be described in some model as a non-deterministic choice, but this is not how we are going to look at it now. There is a very simple reason, is that when you, and there's a point which is not as a good place here, when you differentiate a scalar multiplication of function, then you are going to land on the sum. This might be one of the first rules about differentiation that you learn. You need to sum. You need to first, you need to differentiate one function and evaluate the other one at 0, and sum to do the converse. And this is where co-weakening finds its necessity. For example, if we hadn't defined co-weakening, we wouldn't be able to define the cut elimination procedure on differential linear logic. It's not enough to define co-dereliction, meaning differentiation. If you have co-dereliction and you want to match it with something which was already here, meaning contraction, then you will need the other rules, meaning co-weakening here, but co-contraction elsewhere. So this, hence the necessity to define not only pure differentiation, but also other very basic algebraic rules to describe the cut elimination procedure. And I think until a year ago or 2 years ago, I thought this was completely magical to see how the cut elimination procedure was completely symmetrical, meaning there's no reason why co-dereliction and contraction should interact as dereliction and co-contraction. I know I'm saying things quite quickly, but there's no reason why things should be so symmetrical, but it works really well. I mean, it's the exact same intuitions, like mathematical intuitions, behind the other cut elimination procedure. So this is really nice, meaning what I'm doing sum on something inside the domain of something which used to be a linear map. And well, I'm going to do the sum just at each part of the map, and I want weakening for typability reasons. Okay. So it's really beautiful. I described that in sequence calculus. I do think it might be better described with nets, but I think Luc is going to speak about nets, and Luc just had a stroke because I mentioned his name. Luc is going to tell you everything about nets, where this was first defined, and this talk is going to be on Thursday. It's also very well defined in a categorical setting about which Jean-Simon is going to tell you everything about tomorrow. So yes, everything works extremely well, and this is the first version defined by Thomas Erard and Régnier that you will find in the paper that I should cite at some point, but I don't know where the citation is. I think I put every citation at the end. This is what you will find in a proofnet version in the first paper by Thomas Erard and Laurent Régnier. Okay, so what's missing here? The promotion rule. And I think because you seem all very concentrated, I think I want to go into this cut elimination procedure. We should do that. You should do it at least once in your life, and we are going to do it now. So, yeah, it all works very well, and I think this is the reason why promotion wasn't put in the first version of differential linear logic, because when higher order gets in the way, it's not as simple as it used to be. So we need to define what will happen when we mix Diracs and co-dereliction. So what happens when you allow nonlinear functions to compose and when you want to differentiate them? That's the good old chain rule, meaning describing what's happening when you differentiate a composition of function. And there's a lot of paper. There has been a huge amount of papers at Popper or Leaks this previous year talking about this chain rule, because differentiation is non-functorial. This gives you interesting algorithm explaining how exactly you can compute differentiation. I think Michele's talk on Thursday will be about this different way to compute the chain rule, but we still have to deal with it now in differential linear logic. So this describes the interaction between the promotion rule and the co-dereliction rule, and we need to turn that into a cut elimination rule. So let's go. when we make codirection and promotion interact, we will need to describe we will need to write that in sequence calculi, in sequence calculus. And for that, we need to just go just a tad more into what we can do about distributions. What we can do about distributions, we can do convolution. What example of distribution do we have? We have two, Diracs and differentiations. When we mix two Diracs, we sum into the domain of the Diracs. When we mix two differentiation, we do differentiation at second order. When we mix one Dirac and one differentiation, then we are just translating the function. So instead of differentiating at 0, we will differentiate somewhere else. And this is exactly what allows you to describe the posture. This is exactly what allows you to describe the non-functorial way of differentiation, meaning I can do differentiation at 0, but using the co-contraction, I can also do differentiation at another point. So I am able to describe the facts that differentiation keeps in its memory the point where it should be differentiated. We are able to translate functions, so we are able to translate at other points. So using an informal categorical language, this could be described as that. And using proofs, it could be described like that. And I'm just doing it in a simplified way because I don't want to describe all what's happening in the context, and this is why one should use nets, I think. Okay, so you just had an introduction to differential linear logic. Differential linear logic is about introducing symmetric rules of 3 out of the 4 exponential rules that are defined in linear logic. They are called co-something, co-weakening, co-contraction, co-direction. Co-direction is the most important, but the other ones are extremely important also. The other ones are strictly necessary to describe the dynamic and to make sure that we are indeed differentiating proofs. And my personal opinion that this maybe challenges the interpretation of terms of resources. Like, it's interesting to have other interpretation of Bang, not only in terms of resources, but also in more general languages that are too general for that, but that are also very well described by the algebraic setting of differential linear logic. So, I did syntax for like half an hour, so I'm exhausted. And now I want to go into denotational semantics. So I'm not that sure that differential linear logic is a system for describing proofs. It's more like a type system for describing programming languages that has not yet been defined, or I don't know, a language to define nice categorical structures that allows you to describe well old math and to create new math. I'm not really sure. I think I'm happy to take any opinion about what the status of differential linear logic is. A version of linear logic that gives you a great algebraic setting in which to reason about higher order differentiation. But like models of differential linear logic are a big part of the story, to say the least. And why are models a big part? Because differential linear logic was created because of a study of some models of linear logic. So that's the old idea is that by studying a specific model of lambda calculus, Girard invented linear logic by looking into vectorial models of linear logic. Laurent Régnier and Thomas Erard were able to define differential linear logic. So I very much want to tell you about those vectorial models, the models which were at the origin of the idea, hey, let's differentiate proofs in linear logic. And it's also interesting to go and look what happens here, meaning what are the models that we are finding once differential linear logic has been defined, because this might be the way to continue the tower here, and if we are lucky enough to go back into programs, even if that's a whole other story that I won't be speaking about today, but that you are hearing during the whole week. relational model. I almost don't want to speak about the relational model because I think you will hear a lot during Guy's talk, which is tomorrow. So you will hear a lot. You heard about it this morning, I guess, a bit. The relational model is the model where you will first learn about the notion of resources. Why? Because it is in this model that the exponential is interpreted as a set of multisets. It is in this model that you can see in the semantics the notion of resources which is happening. But in this model, differentiation is possible. It is a bit trivial, it's a bit straightforward if you don't have coefficients, because everything is extremely symmetrical, meaning, so the idea is that formulas are interpreted by sets and proofs are interpreted by relations, and like direction maps a singleton with the item inside it, and codirection maps an object with its singleton. So it is really differentiation. It is a model of differential linear logic, but maybe we can find a bit more, and I don't think it would have been possible to invent differential linear logic with only this kind of objects. You need to go into models which are a bit richer.
I think that the key point is that A dual is equal to A.
Yeah, I should have told that, yeah, sure. And even earlier, A dual is equal to A. You don't learn anything by going into the dual, and so you have no hope. So that's very nice. So let's start to do, we were very much algebraic before. Let's start to do just a bit of analysis. And the first thing to do in analysis when you're in high school or at the beginning in the faculty, before going into functions, you are going into sequences, converging sequences. And Kötter spaces, which were the model that was studied by Thomas Erard, are spaces of sequences. They are in fact good spaces of sequences. These are spaces which were studied before in the 20th century. I don't have the exact date, by people like by Kötter, but they are also described by Schaeffer and people like that. They are called perfect sequence spaces. And why? They are perfect because they are models of classical linear logic. So something is perfect when duality is well interacting. I am trolling intuitionistic linear logic all the way here. So, so you have a good duality notion, and it's a very interesting duality notion because duality comes from the sums, meaning the dual is going to be also a space of sequences, and it's going to be the space of sequences with which interact well, which gives you converging sums when you map them with sequences from the original space. That's an orthogonality notion. That's the duality notion that we are going to use to interpret linear logic. A perfect sequence space is a space that is equal / isomorphic. I wouldn't know how to tell you that. To its bidual. Continuous linear maps between sequences are like kind of matrices. Infinite matrices, or matrices without a unique bound, but there are some kind of matrices which are telling you how sequences interact with one another, and sequences that give you converging sums, absolutely converging sums. They are topological notions, topologies on topological vector spaces that are arising here, but I won't go into the details of that. Okay, and the idea here is that, so linear proofs are matrices, nonlinear proofs are power series. So you can describe what is the power of a sequence indexed by a multiset. So you are going to define the exponential in a way that non-linear maps are going to be described exactly by power series. And the very, very, very nice thing about power series is that they are easy to differentiate. If you want to find the differential of a power series, you just take its linear term. And the linear term is already here. And I think that this is a clear way to see that differentiation is happening in our setting. meaning it's easy to differentiate power series, I would say. And in that setting, codirection can be described as just taking the linear part, meaning the part indexed by singletons. And I hope there's no typos here. Okay. And there are another version of Köthe sequence spaces, which are not vector spaces on the reals, but vector spaces on discrete fields. And it's very interesting, but I won't be talking about that. There are also models of differential linear logic. And the interesting part is that at last coefficients are happening here, and you will see more about that into weighted models, I think. I hope. Okay, so now we are going a bit up in the diagram I showed you. We are going to look into models of differential linear logic which were defined after differential linear logic was invented. Well, not exactly. I'm going to speak about convenient vector spaces. Convenient vector spaces are mathematical objects which were studied independently by mathematicians who were interested into describing differentiation at higher order. Meaning in math, we all learn how to differentiate these kind of functions, but differentiating higher order functions, meaning functions operating on spaces which are maybe infinite dimensional, differentiating functions which are going to be applied on functions, typically, that is not trivial. So mathematicians did their jobs, they did math, and it works well for us because we just have to twist their math and use it, and it gives us models of differential linear logic. Convenient vector spaces are vector spaces endowed with not a topology, but a boundology, meaning a way to describe bounded sets. Proofs are interpreted not by linear continuous map, but linear bounded maps. It's a bit different. It works a bit better, in fact. And functions are smooth. And this notion of smoothness, which is being smooth, is mapping every smooth curve to a smooth curve. It is really what makes differentiation at higher order works well. So convenient vector spaces are extremely interesting objects. What's interesting for us is that it is the model of intuitionistic differential linear logic this time, in which you can really see these intuitions about distributions and Diracs. The exponential is not that much about resources, taking a bags or taking exponents. It's not that much about approximation, then it is about discretization. The exponential is going to be interpreted as all the distributions which can be defined from Diracs, which are, so distributions are the ones which are generated after we take the vector space generated by Diracs, and we complete it, like we take all the limits for a good notion of limits and of complete spaces. So I won't go into the details, but that's a very beautiful object in which you can do a lot of math, and the interpretation of differential linear logic in this setting really describes what I was talking about informally before. I was telling you, hey, co-contraction is about summing the Diracs, blah, 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 blah. In this model, it is. So this is really the model where it's easy to handle functions and distributions. So Kriegel and Mikor were the one to, Froliker, Kriegel and Mikor were the one to describe convenient vector spaces. Riegblood, Thomayrar, and Christine Tasson were the one to make it turn into a model of differential linear logic. You can also make it conjunctive, and you can also make it models of classical linear logic, but it's not easy. It's not an easy task to do. Do I have time? Yes, I can continue. Okay, if I have time, I want to tell you just a bit more about the lambda calculus version of what I've told you about. So differential lambda calculus was as invented at the same time than differential linear logic from the same spaces. It describes the exact same rules than differential linear logic, but for lambda terms. So just so you have a view and of an idea of this syntax, because you might encounter it in the wild sometimes. Let's let's describe it. So now after Julio's talk, you all know about lambda calculus, at least. Differentiation is about describing another way of applying a lambda term to an argument. It's about giving, you had application, now you have linear application. If you need to define a new way of applying terms to functions, terms to arguments, then you need to define a new kind of substitution. So you had good old, I don't want to say easy, but good old substitution. You will need to define linear substitution. And linear substitution can be described in a funny way with a notation which is very close to partial derivatives because it works a bit like partial derivatives. The idea is that if you have a term S and you want to replace a linear copy of X by T, then it's a bit like doing a partial derivative along the vector X. And the rules are described a bit like that. The idea of linearity you already have, meaning something in head position is going to be linear, an argument may not be linear. So we will embed these intuitions into the new substitution we just defined. And I think I just want to give you the rules. I don't know, now I have a bit of more time. So let's see what's going to happen here, for example. I have a vector v. I want to differentiate this term / this function, meaning I want to make it linear. I want x to be replaced by v, but only once. I will go and look for x into my term. I might go and look for it in a linear position, then I will just have to replace it by v. But I can also go and replace it later here. But then I'm not sure how it's going to be computed by x, meaning, is there a mistake here? I'm afraid I have a mistake. There is a big, yeah. What happens to f? Yeah. Yes.
But you should remove it for the rest to be
okay. Okay. Yes, sorry. Okay, so I think I don't want to go into that. And I will just explain the basic rule on most simple examples that are as simple as very simple because they are definitions. So let's go. What is linear substitution about? Let's see. So this is a new kind of substitution. I have a variable and I want to linearly replace x by t in y. Well, if the two are equal, meaning if this is in fact the differential of an identity, then I will just replace it by the vector I was given. Otherwise, I am differentiating a constant function, something that does not depend on the variable I want to be substituted linearly, and this is going to give me 0. If I want to substitute into a lambda abstraction, I'm just going to go inside the lambda abstraction. If I want to substitute inside a sum, I will just go into the sum. If I want to substitute into an application, then this is where the chain rule is going to happen. Differentiating a composition is about the chain rule. Linearly substituting inside an application of two nonlinear terms is going to be about the chain rule. We might not need to go into the details. You can just see that here you have something that you will not find in math. And here you have something with two differentials. And the two differentials are the two differentials you are seeing into the chain rule. It's a bit complicated, but I think I don't want to go into the details now. Yeah, I think you're all tired. I don't know. You might be tired. Yes. You're not tired. Yes.
I don't understand why you have to put the points t everywhere. Like, is it true that d0 of dx is equal to 0 without the t?
Okay. So which rule am I looking at? This one?
Yes, if you remove the t, the point is t.
Yeah.
Yes, is this equation true?
It's not observable anymore.
No?
It's a constant function at 0. So in either case, either it's a constant function which depends on the variable I want to substitute, but when I'm differentiating it, it will lead to 0. If it does not depend on the argument or variable I want to differentiate, it's still going to lead to give 0.
Okay. And on the right, if you remove the point t, like the s plus u.
So here,
If you remove the point t, then you write.
so you're asking if I remove the point t here, it's still, okay, so it's still true, but in fact, for the syntax to be well defined, sadly, you need to make the t part of the syntax. You are not allowed to define partial differentiation as a function for reason of, at least alpha equivalences.
I think it's just a matter of convention. The point is that you define an operation of substitution, linear substitution of linearly substituting t into s or x. So it's notation which is defined by addition. And so you have to in all cases. And in all cases you have to define the function which depends on the variable on the term s and the term t. Sorry.
So the question was, I understood the question to be, could I remove the t here? And my answer was no, but because I think I tried and failed, but maybe...
Okay. Yes.
I think you can just repeat what you said to Jean-Baptiste, because we
No,
have time.
I was just saying that it's just a matter of convention that you define by induction on S a function, okay, and which depends on X and T also. And so you have to do all cases, and in all cases the function takes 3 parameters which are X, S, and T. And you have to say how it deals with it, and that's all.
But my point was that this needs to be an algebraic operation. This can't be a dynamic one. Can't, like, I would love to see that linear substitution becomes a dynamic operation into the syntax, but it needs to be something very, very, that smashes all computations out of your lambda terms and just gives you the result already. Okay, and because I have a lot of time, and I will finish early, but I just want to say a bit more about differential linear logic and semantics. I spent a long time telling you differential linear logic is very beautiful and very mysterious because everything is really symmetrical, and there's a reason for that, and I just understood it a few years ago, like 2 years ago, and I'm extremely happy about it, so I want to tell you about that. Do you remember the Laplace transformation? So those of you who took math lessons, I guess, you had to deal with that a lot. Laplace transformation is something which is very much used in engineering. It's very nice because it turns differential equations into polynomial equations. Polynomial equations are easier, much easier to compute with than differential equations. And the Laplace transformation does that exactly. So it is described that way, but if we want to make it an object of differential linear logic, or if we want to make it a logical object, we want to make it a higher order object. And this description is not very much higher order. Like the integration from 0 to the infinity is not a higher order object. My way, our way to speak about integration is to use the language of distribution theory instead. Integration is used to say that distributions are generalized functions, but the good way to speak about the Laplace transformation is to say, in fact, it is a transformation between exponentials, between a bang and a y naught, and it takes a distribution and it applies it to a function applied to the exponential. The exponential function, not as the exponential connective, but that's the higher order way. And what's very beautiful about that is that it turns differentiation into polynomials. So it turns co-structural rules into structural rules. And the interpretation for weakening, contraction, and dereliction is exactly the Laplace transformation of the co-weakening, co-contraction, and co-dereliction. So one of the reasons why differential linear logic is so symmetric and everything is symmetric is that behind the two we have an operator, which is good old Laplace operators. The last thing I want to tell you about is that it was symmetrical up to promotion. In fact, we can find the symmetric to promotion. It's called to-digging, it's called co-digging. It works well, and it reconnects us with the quantitative point of view that we had before. Differential linear logic, I did not speak about Taylor approximation at all during my talk. I considered very general functions which might not be equal to their Taylor approximation. I did not need that. When you introduce a co-digging, then the rules of the co-digging tells you that every function needs to be equal to its Taylor approximation. It works well in the models. We don't have cut elimination for this rule when we introduce co-digging in the syntax. So beware, it's not. It doesn't work well. It works well in graded settings more than in the models I just shown you. But there is something called co-digging. It reconnects us to Taylor approximation, even if it doesn't work completely well. And that's the end of my talk. So I'm finishing well in advance, but I hope you're okay with it.
Are there some questions? Yes.
Okay, so it might be a dumb question, but so the Laplace transform W bar into W, C bar into C, and D bar into D. Can you apply it to P bar and obtain P?
Yeah.
Oh, okay.
Yeah. When you apply it, and it's easy to check, easy to take. I could do it now, but it's really to see that, let's look at what this does. What happens if I want to evaluate that at 0, then I will have something which exactly creates a constant function at 1, because exponential of 0 is 1. So this is going to be evaluating a distribution, the dual of evaluating a distribution at a function 1, meaning the function 1. So co-contraction and contraction, well, that's the reason why exponential connexes are called exponential, because they turn additives into multiplicatives. And so when you take a sum, so what's being described by co-contraction, and you put it through the Laplace machinery, you will arrive on a multiplication. So what contraction is about. And differentiation is likewise, because the differential at 0 of the exponential works well.
Okay.
Yes.
Thank you for the talk. You have presented a differential logic and the differential lambda calculus.
Yeah.
So my question would be, can you type the lambda calculus with your logic, and if not, do you know why?
So differential lambda calculus is not typed by differential linear logic, it's typed by minimal logic, because we are never leaving the linear variable free. You don't have linear maps. The linear variable is embedded in the syntax with the partial derivative notation I told you about. It's a hard job of finding a language for differential linear logic. This would be something like L calculus. Like there are languages for linear logic, and they are not that easy to manipulate, and you would need to do that for differential linear logic, but there are notions of polarities that makes it hard, I guess.
Thank you.
can you develop a bit on what you said at the end, that you that with codigging you have a way of Taylor expanding? Because on the one hand you don't have cut elimination. On the other hand, like you can already ask in any model you can ask for your interpretation to like for the interpretation of a term to be exactly equal to the Taylor expansion of the interpretation of the resource terms, if you want. Okay, and this is a way that you can say that your model models the Taylor expansion. Okay, and you also, if I remember correctly in your paper, you also have something like this. You say something like, okay, my model like is compatible with the Taylor expansion, but I don't know if it's the same thing or if it's a different.
So there are several things indeed. So when I say we don't have cut elimination, we have almost everything because it all works well. So it's all going to be symmetrical to what happens with promotion. The only thing is that we don't have the cut elimination between digging and codigging. Promotion and we spent a few hours on that with several people, and it's not obvious what should be the solution here. The other issue is, of course, you have a lot of models in which functions are equal to the Taylor expansions, but to have a model of that, you need that to be definable. You don't only need this to be computable, this to be true. You need this to be a map, and it's very strong, in fact, to ask that this converge on every distribution. And for example, in Cutter spaces, it doesn't work. Sadly, because it's you can say that codigging is going to transform a distribution that applies to a certain type of functions into a distribution that applies to another type of function. So there are great stuff happening here about bounding the convergence of your functions with exponentials. I'm sorry, exponentials are everywhere, but you can't say it's always going to converge, and in particular, and this was found by Thomas Erhard, it doesn't converge on the exponential of an exponential.
So you're saying that this is asking convergence of that series is a way of asking interpretation of the terms to be analytic?
So that's a morphism that we could define abstractly if every sum converges, and let's suppose that every sum converges, then the same way that promotion and dereliction form a comonad, codigging, copromotion, and codereliction need to form a monad. Yes, a monad on bang. And what this monad is going to tell you, the laws of the monad, when you compute it, like this one, gives you exactly that the exponential of the differentiation is the identity, but the exponential of the differentiation operator is exactly the Taylor expansion. It's exactly taking the sum of the nth derivative. The exponential is the sum of the nth power with a coefficient. The Taylor expansion is the sum of the nth derivative with a coefficient. And the law of the monad tells you if this is to be true, then every function needs to be equal to its Taylor differential at 0. But it's easier to have that at every point than to have this to be a general definable morphism in your model.
Okay, so like adding a codigging and having all this is a way of having the fact that the interpretation of terms are analytic functions. This is
Okay, the tentative was to make differential linear-logic symmetric. It works until a point, but what works is that it gives you a monadic presentation of quantitative semantics in a very plain way.
Okay. Nevertheless, you can still ask for this analytic condition without bothering about coding.
Yeah. We could ask, and Sorry? Cutter spaces work for that, but don't have coding. Yeah.
Okay.
But they have Taylor extension.
Okay. Thank you.
Are there other questions? Oh.
I mean, a really small question. Do you have any characterization of the Laplace transforms that you use? I mean, because it sounds like Laplace transform should have some sort of property that it is a unique transformation that does blah 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 in order to have that or something. I mean, or
So
like in the proof, do you only use the computations and never?
So
I don't know.
What
I don't know. It's completely
Jean-Simon-
open-ended, so.
So this is work with Jean-Simon Pacolomé, who's here. What Jean-Simon told me, I think, but maybe I'm wrong, that this is some kind of a mixed rule. The idea is that it transforms a connective into its dual, and that's a mixed rule. I don't know, it's something like that. Otherwise, you can describe it, you can axiomatize. This was also work by Jean-Simon, which axiomatized in a categorical way what's an exponential, and you can either first define the exponential and then what's a Laplace operator, or do it on the other way. First define what's a Laplace operator and define an exponential. So if you have a way to speak about differential linear logic, then you have a way to speak about what's an exponential and what's a Laplace transformation. And you can prove that it does transform indeed in the models co-structural rules into structural rules. The thing is that, I don't even know you know that, but it's quite easy to go from that way to that way, but finding the inverse is a lot harder. So I'm not saying at all that from any model of linear logic you can have a model of differential linear logic, but when you have a model of differential linear logic, you can link it to its linear logic part. So that's all.
By the way, in the Laplace transform, f is one of your nonlinear functions?
Yeah.
Or? Okay.
F, because, yes, f is, yeah, maybe I should have changed, I don't know. So f, yeah, because in fact, here f is a nonlinear map, but I want to understand it as a distribution.
Yes.
So here it's going to be the distribution that takes the act on a function by doing the integral.
Yes.
So I want to replace f by
yes, that's clear.
phi
yes.
here,
Yeah,
and
yeah,
this
yeah.
is just going to be phi.
That's clear, yes.
That's the way to see it, yeah.
Absolutely, yes.
So I don't know, the link here is that usually distributions are described as general functions, and if you have a function f, then you can turn it into a distribution, meaning you can make it act on linearly on other functions by taking the integral, and that's the link between the integral and distributions here. This is why I'm saying, hey, this is not higher order. To make it higher order, let's consider Brang.
Okay. More questions? Okay. Thanks again.
Thank you.